Imagine the universe in all its vastness and complexity. Galaxies swirl, stars explode, and planets orbit in a delicate cosmic dance. Calculus is the language we use to understand this ever-changing universe. It is the mathematics of motion, of change, of growth and decay. Calculus might seem intimidating at first, but it's really just a way of describing how things change over time. Just like astronomers use telescopes to study distant stars, mathematicians use calculus to study the intricate patterns of our world. From the smallest atom to the largest galaxy, calculus helps us make sense of the universe around us. It allows us to predict the trajectory of a rocket, the spread of a disease, or the growth of a population. So, buckle up and get ready to explore the fascinating world of calculus. It's a journey that will take us to the very heart of change itself. Change is the only constant in the universe. Planets orbit, seasons change, and even our own bodies are in a constant state of flux. Calculus provides us with the tools to quantify and understand this dance of change. At the heart of calculus are two fundamental concepts: differentiation and integration. Think of them as two sides of the same coin, each offering a different perspective on the nature of change. Differentiation allows us to zoom in on a specific moment in time and measure the instantaneous rate of change. Imagine a car speeding down a highway. Differentiation allows us to determine the car's velocity at any given instant. Integration, on the other hand, allows us to take a step back and look at the big picture. It allows us to calculate the total accumulation of change over a period of time. In the case of our speeding car, integration would tell us the total distance traveled over a certain time interval. At first glance, differentiation and integration might seem like completely different concepts. But in reality, they are intimately connected. They are two sides of the same coin, each providing a unique perspective on the nature of change. Imagine a graph representing the velocity of a car over time. The slope of the graph at any given point represents the car's acceleration at that instant. This is precisely what differentiation allows us to calculate: the instantaneous rate of change, which in this case is acceleration. Now imagine wanting to find the total distance traveled by the car over a certain time interval. This is where integration comes in. Integration allows us to calculate the area under the velocity time graph, which represents the total distance traveled. The fascinating thing is that differentiation and integration are inverse operations. This means that if we differentiate a function and then integrate the result, we get back the original function. The profound connection between differentiation and integration is formally established by one of the most important theorems in mathematics, the fundamental theorem of calculus. This theorem serves as a bridge between the worlds of instantaneous change and accumulated change. The fundamental theorem of calculus comes in two parts, each revealing a different facet of this connection. Part 1 states that if we define a function that represents the accumulated area under the curve of another function, then the derivative of this new function is simply the original function. In simpler terms, it tells us that the rate of change of the area under a curve is equal to the height of the curve at that point. Part 2 of the fundamental theorem provides us with a powerful tool to calculate definite integrals, which represent the accumulated change of a function over a specific interval. This part of the theorem states that we can find the definite integral of a function by simply evaluating the difference of its antiderivative at the endpoints of the interval. Section 5. Unlocking area with integrals. To truly appreciate the elegance of the fundamental theorem of calculus, we need to delve into the concept of integrals. Imagine trying to determine the area of an irregularly shaped object. Traditional geometric formulas fail us in this endeavor. This is where integration comes to the rescue. Integrals allow us to calculate the area under any curve, regardless of its complexity. The integral of a function represents the accumulation of infinitesimally small rectangles that fit under the curve. The definite integral, denoted by the symbol, represents the area under the curve between two specific points, called the limits of integration. It's like measuring the area of a slice of the total area under the curve. Section 6. The mean value theorem for integrals, a cosmic balancing act. Before we can fully unlock the secrets of the fundamental theorem of calculus, we need to understand a crucial concept, the mean value theorem for integrals. Imagine a celestial object like a star emitting varying amounts of energy over time. The mean value theorem for integrals tells us that there exists a specific point in time where the star's energy output is equal to its average energy output over the entire period. In mathematical terms, the mean value theorem for integrals states that for a continuous function over a given interval, there exists a point within that interval where the function's value is equal to its average value over the entire interval. This theorem guarantees the existence of a point that perfectly balances the function's values over the given interval. Section 7. The Fundamental Theorem, Part 1, Unveiling the Derivative. Now, let's unravel the first part of the fundamental theorem of calculus. This part establishes a profound link between the seemingly disparate concepts of differentiation and integration. It tells us that the derivative of a function that represents the accumulated area under another function is simply the original function itself. Imagine a graph representing the velocity of an object over time. The area under this graph represents the object's displacement or the total change in position. The Fundamental Theorem of Calculus, Part 1, states that the derivative of the displacement function is simply the velocity function. In other words, the rate of change of the accumulated area under the velocity curve is equal to the velocity itself. This might seem intuitive, but its implications are far-reaching. It highlights the inverse relationship between differentiation and integration, demonstrating that they are two sides of the same coin. Section 8. The Fundamental Theorem, Part 2, Finding the Area Under the Curve. The second part of the Fundamental Theorem of Calculus provides us with a powerful tool to calculate definite integrals, which represent the accumulated change of a function over a specific interval. Instead of resorting to tedious Riemann sums, this part of the theorem allows us to evaluate definite integrals by simply finding the antiderivative of the function. An antiderivative, also known as an indefinite integral, is a function whose derivative is the original function. The Fundamental Theorem of Calculus, Part 2, states that to find the definite integral of a function over a specific interval, we simply need to evaluate the difference of its antiderivative at the endpoints of the interval. This part of the theorem significantly simplifies the process of calculating definite integrals, making it an indispensable tool in various fields from physics and engineering to economics and finance. Section 9. The Power of the FTC Real-World Applications. The Fundamental Theorem of Calculus is not just a mathematical curiosity, it's a powerful tool with countless real-world applications. From predicting the trajectory of a rocket to modeling the spread of a disease, the FTC plays a pivotal role in our understanding of the world. In physics, the FTC is used to calculate work, energy, and momentum. In engineering, it's used to design bridges, airplanes, and other structures. In economics, it's used to model economic growth and predict market trends. The FTC is a versatile tool that allows us to solve complex problems in a wide range of fields. Its ability to connect differentiation and integration makes it a cornerstone of modern science and engineering. Section 10. The Enduring Legacy of the FTC. The development of calculus, and in particular the fundamental theorem of calculus, marked a turning point in the history of mathematics and science. It provided scientists and mathematicians with a powerful new language to describe and understand the universe. The FTC paved the way for countless scientific and technological advancements, from the development of classical mechanics to the advent of modern physics. Its impact on our understanding of the world is immeasurable. Even today, centuries after its discovery, the FTC continues to be a cornerstone of mathematics and science education. It is a testament to the power of human ingenuity and our enduring quest to unravel the mysteries of the universe. Section 11. Conclusion: A Universe of Possibilities. As we conclude our exploration of the fundamental theorem of calculus, it's important to remember that this is just the beginning of a much larger journey. Calculus is a vast and fascinating field with countless avenues for exploration. Whether you're a student just beginning your mathematical journey or a seasoned scientist seeking to solve complex problems, calculus offers a powerful set of tools to explore the universe around us. So embrace the challenge, delve into the world of calculus, and unlock a universe of possibilities.